Okay, so having seen some graphs in the previous video, now I'd like to go into one more thing that we need to be able to do with parametric equations, which is to just change them from parametric form to Cartesian form and vice versa. If you're given a parametric equation and you want to stick it into Cartesian form, what you want to do is you want to eliminate the parameter t. So pretty much all you want to do is solve for t and substitute into the other. Starting with our easiest example here, and we know this is a line, okay, because everything is linear. So the easiest thing for me to do is just to solve for x, to solve for t in terms of x, right? So t equals x minus 1, and then I'm just going to substitute that back into here. So I have this. And then I basically get minus 2x, what? Plus 7, 5, 6, 7, okay? The only other thing is this, okay, for maybe not for all x though, t goes from -2 to 3. So if t equals -2, x then is going to be -1. And if t is 3, then x is going to be 4. So this is only the piece of this bit up here is only the piece of the line where x goes from 1 to 4. Now I actually don't remember, I think we did -5 to 5, but whatever, that was supposed to be that. That's fine, whatever it is, you get the idea. So you would end up with this piece of this line, okay? Not hard. When it comes to, say, a circle, let's say this is a parametrization of a circle, okay? With t, and I'll do 2 pi. You'll notice there's a 3 here. So what this really means, if I put it into Desmos, it will still look like that circle, unit circle. There's no coefficient there. However, what's going to happen is it will go around 3 times because of this 3. But you can't really see that. In any case, what do I do with something like this? Something like this, it's a little bit more complicated because you don't want to do the inverse anything. Definitely try to avoid, if it's got cosine, sines, tangents, something like that, you want to avoid trying to solve for t. You want to use some nice trigonometric formulas. Here, of course, we know that cosine squared 3t plus sine squared 3t is 1, right? So that gives you y squared plus x squared equals 1. So you can see now that it is the unit circle, and I've gone around it 3 times, however many times. Okay, so I'm just going to say unit circle, good enough. Now, you saw we also did one that had a radius of 2, okay? So how does that work? Let me see. We had x, I forget what it was, but I'll just put up 1. I'll just put up x equals 2 cosine t, and y equals 2 sine t, okay? Well, you still want to use our friend, the Pythagorean identity, but now it's a little bit wonky because it's got the 2 in it. So really you want to solve for something, but you don't want to solve for t because you don't want inverse crap. You want to solve for cosine of t is x over 2 and sine of t is y over 2. Now it's no longer the unit circle, right? But I can substitute these into there and I get x over 2 squared plus y over 2 squared equals 1, or x squared plus y squared equals 4. So I have a circle of radius 2. So anytime you see this with a number out there besides 1, that's going to be the radius of the circle, and precisely this is the reason why. Now this reminds me also of the other problem we did with the ellipse. We drew an ellipse. Where did it go? Here it is. The ellipse was this. This was the equation of the ellipse. And first we had the whole thing, and then we just had some piece of it. No, it was a 3 cosine t. Okay, so you see this is sort of similar to the circle, but not, right? Because it's got the 3 and the 2, and it's got this 1 and the 4. But still, because we see the cosine and sine, we want to try to somehow shove that into here. So let's solve for cosine t and sine t. And y minus 1 over 2 is sine t. So if I put those in there, I get this. Now, and that is what it is. And that is done now. You can't do any more with that, right? Because I've got the 9 and the 4. It's not like a circle where those are the same. Okay? And the other thing you'll notice is that it's got this x minus 4, y minus 1. If you remember the picture, this guy was somewhere out here, right? It had a center of x equals 4, y equals 1, semi-major axis of 3, and a semi-minor axis of 2. Of course, if you don't remember the equation for an ellipse, it's not the hugest deal in the world. I just wanted to show it to you because it does sometimes pop up. Most importantly, circles, you're being able to parameterize a circle, so recognizing that it is a circle, or alternately, if you're given a circle, being able to parametrize it. So, in other words, going backwards from what we did. Because what we did now is eliminate the parameter. Now, the second thing we want to just mention briefly is what happens if you have a curve and you want to parametrize it. So, let's say I have something like this. All right, this is some parabola, right? And I'm taking x from -2 to 2. Easiest way to parameterize, whenever you have y given as a function of x, easy. You just let x be the parameter. You let x equal t. Then y is 3t squared plus 2t minus 1. T goes from -2 to 2. Easy. So why would you even bother to do that? Well, you really wouldn't bother to do that often, for sure. Sometimes you might need to, but for the most part, if it's y as a function of x, you're good. If it's the other way, though, let's say it's x as a function of y, right? And this is also a parabola, right? But it's on its side, right? Oh, when x is like this. Wait, is that right? It might go the other way. I always get these wrong. Okay. Oh, yes. That's right. Okay, so this would be negative 2. I always get them opening. I have a hard time picturing it. I'm so used to doing it the other way. All right, so this again is not a function. But it's not a big deal. We've been doing stuff with this all the time. But if for some reason you wanted to parameterize this, you could do the same kind of thing, but it would be much easier just to rather than letting x be something, let y be your parameter t, and then x is t squared minus 2. And I didn't give you a, let's say, yeah, well, never mind. So whenever you can figure out whatever part you wanted, whatever part you needed. Say, in this case, if I want it everywhere, I would just be taking t from negative infinity to infinity. By the way, you can always do that as well. Okay. We will use the equations for things like the cycloid sometimes, just because it's an interesting example. I will not expect you to remember any of those. So if we were doing something with it, or also even with the, if we're doing anything with the cycloid or anything fancy like that, I would give you the equation.